All right, so we want to write the mass action expression for this reaction. So here's a reaction. It's in equilibrium. We have reactants and products. How do we write the mass action expression? Do you remember?
The notes was like, you take the products.
Right, products. So N2O4.
Now, is it the concentration of them?
That's right. Those little brackets mean the concentration of those products.
And you raise it to the coefficient. It's just one, though, right?
That's right. Just one on here, coefficient here.
And then you divide it by NO2 concentration squared.
Very good. NO2's concentration squared. That would be my mass action expression. Excellent. How about this one?
Let's see. It's going to be concentration of carbon dioxide squared over concentration of oxygen times concentration of carbon dioxide squared.
Okay, very good. Exactly. Concentration of carbon dioxide to its coefficient over concentration of the reactants to their coefficients. Okay, you work on this one at home. Write it down. Make sure you're not missing anything. Push pause. Okay, what is it, Fred?
Concentration of ammonia, that's NH3, squared over concentration of hydrogen gas cubed times nitrogen gas to the 1.
Okay, like that?
Yeah, that's what I meant.
Excellent. Good job. Okay, another one for the folks at home. Which one is right? Take your time and find the right answer. Did you get it, Fred?
Yeah, I think I got it.
Which one's right?
Well, I think it's going to be C, right? Because the concentration of ammonia has to be to the 4th, and it has to be, oh, no, sorry, it has to be A, concentration of ammonia to the 4th, and it's on the bottom because that's reactants.
Okay, very good. Good job. C is incorrect because the products should be on top. B is incorrect because ammonia has to be to the 4th, raised to their coefficients. Okay, excellent. So the Q value tells us what the equilibrium condition is at the current scenario, the current condition, right? So I have a chemical reaction here. It's inside this balloon. The Q value, whatever it is, maybe the Q value is 0.0001, all right? That tells me the current equilibrium condition in there. Now, if I have a Q value of 0.0001, what does that mean about reactants to products? I don't know what the reactants and products are for the reaction. So let's just make something up, right? I don't know what they are. But if I have a very low Q number, what does that mean?
I can't remember what a low Q number means.
Well, remember, the Q mass action expression is products, which in this case is Y, over reactants, their concentrations raised to lowercase x and lowercase y raised to their coefficients, which, looks like 1 here, but whatever they are. So if this Q value is very low, then that means, what do we have to do to get a really tiny number here? To get a really tiny number here, you need to have a low number on top and a high number on the bottom. So that means if it's low, then what?
Oh, that if the high number on the bottom, that means there's mostly reactants.
Very good, mostly X. Okay. So if I gave you a Q, a very low number about the, oops, this is an equilibrium, about the equilibrium of this reaction, then it tells us right off the bat, very low number, oh, there must be lots of reactants, right? Lots of high concentration of reactants. Okay. If I had a very high number, that would mean lots of products. If I had a number that was close to 1, that would mean very similar concentrations. That's the Q value. Now I'm going to introduce to you another value, which is the same thing, but it's the K, big K, called the equilibrium constant. And it's what we expect from previous experiments, what we expect the equilibrium to ultimately be once dynamic equilibrium is obtained. Okay? So, Q tells me that currently in this balloon, we have mostly reactants. But if K is equal to a large number, like 10,000, then that means that this reaction is not at equilibrium. And to get at equilibrium, X is going to have to, well, if I have a large number, if that is going to be my equilibrium once the reaction reaches equilibrium, then what needs to happen to go from the current condition to this condition?
Well, if you have a big number, that means that you have lots of products, right?
That's right.
So to get to lots of products, lots of X is going to have to be converted to Y.
That's exactly right. So we have one number that tells us about the equilibrium, and then we have a second number, or the current equilibrium. We have a second number that tells us about what the mass action expression value will be once we reach equilibrium. And from those numbers, we can tell whether the reaction is going to have more reactants form or more products form. Let me give you another example here. Some chemical reaction, right? Some balloon where this reaction is proceeding. Okay? The Q for this reaction is, we're starting off with, what does that mean? Do I have lots of X in here or lots of Y in here if I have a very low Q value?
Oh, I can't remember. How did you do that again?
Well, remember, the mass action expression is the products over reactants, their concentration. So I'm going to put in ones here because it looks like I have ones on it.
Okay, so if it's very low, then that means Y has to be a small number and X has to be a large number. So it's very low, so X is pretty much the only thing in the balloon, or it's the highest in concentration.
Very good. Now, if I say my K is equal to 0.01, all right, under this condition, what is going to predominate, X or Y?
Well, it's still low, so that means there's going to be still more X than Y, right?
That's right. But here I have a lower Q value, so some X is going to react, but there's still, in the end, going to be mostly Y, because apparently, I forgot the arrow again, Y decomposes faster than X forms into Y. So this relationship between Q and K tells us about how the reaction is going to proceed under the current conditions. All right, now, equilibrium occurs, right? Reactions go from A to B. Whoops. If I have a reaction, though, where A, which is, let's say, aqueous, is combining with B, where B is a solid. Whoops, that changes this reaction. And we're forming C, which is aqueous. Well, if this reaction is occurring as it's written, and we have B in some container, and it's solid, so there's some solid B here, and A is dissolved in water, it's aqueous, right? If we change the concentration of B and put more solid in here, that won't influence the reaction's equilibrium. Because if it's solid, that means a high percentage of that material is not able to react. And increasing that concentration of solid isn't going to change the rate of this reaction. That might be hard for you to understand, but it's essentially the solid, when you increase the amount of it, you change the surface area that you've added in there as well, and you're adding more stuff, but also adding more stuff that can't react because the surface area is contained within inside the solid material. So, additionally, if a liquid, so if C, another product here was liquid, it's the same thing. Because if I want to increase the amount of D, let's say D is in here as well as a liquid, if I want to increase the amount of D in my reaction by pouring more D into it, it actually will also change the volume. And so the availability of D will not increase. if I have something that's liquid already floating around in here, and I add more liquid, it will actually dilute everything else, and it won't actually increase the amount of D that's available. And for this reason, solids and liquids are not included in equilibrium expressions. Okay? So here's an example of an equilibrium expression. And knowing now that solids and liquids are not included, let's write the mass action expression for this reaction.
What's the mass action expression?
Remember when we would write, for example, A plus B going to C, we would say that the mass action expression would be the concentration of, I'm going to throw in some coefficients there, concentration of products to its coefficient over the concentration of reactants to their coefficients.
Okay. So this one would be concentration of silver ion. No. Products over reactants, right?
Yeah.
Concentration of silver chloride over concentration of silver ion times chloride ion.
Okay, let's check.
What? What's that? Oh, they didn't include the solid. That's right. You don't include the solid. So you just write 1 up there?
That's right. So this is a solid. Adding more silver chloride will not increase the rate at which the reaction goes this direction. Okay, there's already solid hanging around doing nothing, so putting more of it in is not going to make more of this reaction occur. So I just have the reactants on the bottom raised to their coefficients and 1 on the top. Okay, how about this one?
Okay, so concentration of H3O plus times concentration of H2PO4 minus over concentration of, we don't include the water, concentration of H3PO4 minus, or H3PO4.
Very good. Excellent job. And this one here?
Well...
Actually, I'm going to give you guys this one next time as a review. So, see you later. Good job.
Thank you.